In this demonstration, we're going to show how you can model a scissor jack using SimMechanics. This is the system we're going to model. By actuating this mechanical linkage, we can raise or lower a platform. We're going to create this model using SimMechanics. First, we're going to model the mechanical link. The mechanical link has 3 connection points, and we'll create this using a block diagram. This block diagram we will pack into a subsystem so that we can reuse it when we model the link on the other side of the scissor. When we're done with the model, you'll be able to see how we can raise and lower the platform using these linkages. I'll now switch over to the model so that you can see how this is done. SimMechanics can be found beneath Simscape in the Simulink library browser. The first step in defining our scissor mechanism is to define one of the mechanical links used in the scissor. We'll use the solid block to define the geometry, inertia properties, and how the block will be displayed. We'll define our link as a simple brick that is 240 centimeters long, 15 centimeters wide, and 4 centimeters deep. We'll let SimMechanics calculate the mass and inertia properties automatically from the geometry that we've defined, and we'll change the color of this link to red. When we connect this to the world frame, which is our global reference for our mechanism, we can then update the diagram and we'll see the visualization for our link. Again, a simple brick. Our link only has, at this point, one coordinate system located at the center of the link. So we'll need to add other coordinate systems or frames for our attachment points, one at each end. To add those attachment points, we're going to use the rigid frame transform. So the rigid transform defines the displacement and orientation difference between two coordinate frames. So by adding this block, we are adding a frame. We're going to define the difference between the displacement between these two frames to be 120 centimeters along the x-axis. When we update the diagram now, we will see that our link now has 2 frames, one at one end and one at the center. By copying and pasting this rigid transform, we will add the 3rd coordinate frame to our system. So now we can see that it has coordinate frames at both ends and in the center. We're going to want to reuse this link a lot as we build up our mechanism, so we are going to pack this into a subsystem. Going into the subsystem, we can then name the frames by clicking on these port blocks and naming them C for center. We'll name this one F for the front end of the mechanism, and we'll name this one R for the rear end of the mechanism. And to get all the ports on the same side of the subsystem, we'll change this to left. So at this point, we have defined our link subsystem. We'll name this inner link. And when I update the diagram this time, you'll see that the tree browser is going to change. So now the hierarchical changes that we have made in the block diagram are reflected in the tree. The next thing that we would like to do is to make this link pivot like a pendulum. To do that, we're going to need to add a joint. So we'll go back to SimMechanics into the joints library and get a revolute joint. By connecting that between the world frame and the part that we've just defined, we will add a degree of freedom to our model. We're going to connect this to the F port for the forward end of our link, and then to the world frame. Now when I update the diagram, we see that the revolute joint is displayed. When we highlight the revolute joint, we can see in the animation that the z-axis is pointing straight up. If we look in the mechanism configuration, we can see the gravity is pointing straight down. So the degree of freedom being about the z-axis, this link will not rotate like a pendulum unless we change the orientation of this revolute joint. So to do that, we'll go get a rigid transform block and define the difference in rotation between the world frame and the B frame of this revolute joint to be, and we're going to rotate this about the x-axis by 90 degrees. So we'll connect this here. Now when we update the diagram, we can see that the degree of freedom for our revolute joint is in the proper direction, and when we run the simulation, we can see that it swings like a pendulum. The next step for our scissor mechanism is to add the other link of the scissor. So we'll make a copy of our inner link block, name it outer link, and then to connect it to the other link, we'll use another revolute joint. So we'll copy this block here, connect the C ports together, And to make it easier to tell the links apart, I'll come in here and we'll change the color of this link to be yellow. Now when I update the diagram, we'll see that outer link has been added. And when we run the simulation, we can see that the two are moving. The inner link is moving like a pendulum, and the outer link is simply pivoting about its center. We'd like to offset these two links by a distance. We could build up a shaft from the foundation elements. What I'm going to do is I'm going to go to a library of parts that I have defined and grab a predefined shaft part. So if I connect this here, this will add a shaft to my mechanism between the inner link and the outer link. Now when I update the diagram, we will see that the links are now separated by a small shaft. And we can see that when we run the simulation, that it still moves as before. So we could continue to build up our mechanism, either defining new parts to be reused or pulling from the library. What I'm going to do now is I'm going to open up a finished model that uses the predefined parts that I've shown you and has a similar structure to what we've seen so far. When I update the diagram here, we see the complete X as shown, and when we run the simulation, we can see that it will move upwards, again moving the platform up. So we could pack these components into a subsystem, reuse the X on the opposite side, and continue to assemble our mechanism. At this point, I'm going to show you what the final scissor lift would look like after we assemble all of the parts together, add a controller, and a hydraulic actuation. When I update the diagram, you'll see the full 3D mechanical system in the Mechanics Explorer. You'll also see that we have defined a controller. So now when we look at this model, we can see that we have not just one X, but 3 different stages. And if we go into the model itself, we can see that we have an actuator that is defined in SimHydraulics and SimScape that is connected to our mechanical mechanism. So if I go back up to the top level and run the simulation, we'll see that the scissor mechanism or the scissor lift will extend. Again, driven by the controlled by the controller and driven by the hydraulic actuator that I've shown you. So in this demonstration, you've seen how to build up parts in SimMechanics, connect them with joints, and then reuse those subsystems in a full model containing the controller and the hydraulic system.